record button, and then I'll share my screen. Okay, so this is just the Discord here. Okay, I need to get rid of this. Okay, so this past week, the contest that I set up is a regional contest from 2015 from our region, so you can get some idea of what this problem is like. Maybe you shouldn't trust these times for Dustin, because he's not somebody that, well, nobody can submit and get 8 problems accepted within 5 minutes, because he has done this before. So he just probably just grab the files and we submit them. Okay, so don't get scared because of that when you see, oh my God, this person solved so many problems. Now, it looks like A is easiest, because most people, not everybody, but most people that tried it eventually got it. And then, you know, maybe J, it's also not so bad, and maybe D is okay. And then there's some problems that are harder. So with a small group like this, it's not so easy to tell. But when you're actually in a real contest, especially if the scoreboard is being updated real time, then you will start to see, you know, after maybe, let's say, you know, 20 minutes in a contest, maybe you're new, so you're not that fast. And 20 minutes in a contest, you see, you know, 10 teams have solved A and nothing else. Then you know that A is probably the easiest problem. There's no guarantee that the problems are sorted in any order of difficulty. The easiest problem can be somewhere in the middle. But, you know, if you see after about 20 minutes, everybody is solving a particular problem, then you know it's probably easy. And conversely, if you're working on a problem and you see, all you see is either nothing or a whole pile of people submitting and getting red, then maybe it's not as easy as you think. Okay, so in a programming contest, again, for those of you that don't know, how does it work? You are ranked based on the number of problems you solve. Okay, so if you solve 9 problems, you're ahead of somebody that solved 6 problems, and so on. And it doesn't matter if you solve the 9 easiest problem or if you solve 1 really hard problem. If you solve the 1 hardest problem, it is still not as worth as much as the one that solved 9 easy problems. Okay, so usually you want to solve easy problems first. And then what about these numbers, the time? The time is the number of minutes from the time of the start of the contest to the time you got a correct solution. So normally you would never get, you know, 14,000 or 1,400, because the contest usually is only 5 hours long. So it's 0 to 300. And then basically from the start of the contest to the end, to the time you get an accepted, that's the time for that problem. If you have incorrect solutions, so for example, here Caleb has 2 incorrect submissions before the 3rd correct one, then it's whatever this time is, 7196, plus 20 minutes for each incorrect. So every time you get an incorrect, you get 20-minute penalty when you finally solve it. If you never solve it, then you don't get that penalty. Okay? But it's still always better, even if you have penalty, it's always better to solve the problem, because solving the problem will give you higher ranking, right? Okay, so that's kind of a very quick overview of how this thing works. So maybe I also want to show you now the actual contest back in 2015 when we actually had the regional contest. So this is 5 hours long, 3 people. How did people do? And this is the actual scoreboard at the end. So you see A, so if you look down the list, the first team that solved A took 5 minutes. Okay, so U of A that year, one of the U of A teams solved it in 5 minutes. And then if you go all the way down, it will tell you also, for example, A, out of 100 teams, sorry, out of 100 attempts, 49 of them were correct. And lots of teams solved it. Then D, 45 teams solved it. F, 29, J, 50, and so on. So by looking at how many teams solve something, you can guess, you can look at that and you can say, oh, this problem is probably really hard. If, for example, G, nobody solved it, and C, nobody solved it. B, only 2 out of 90 solved it, so it's not that easy, and so on. Okay, but of course, you don't have that information if you are doing a contest in real time, but you'll see this scoreboard evolve as the contest goes. Okay, so what I want to do today, I want to show you, I want to talk about the problems sort of from maybe the easiest to hardest. for the ease, so one of the things that maybe I want to say is I'm not actually going to show you the code. The reason is that for those of people that are actually taking the 3200 course this term, this can be part of the course project. So I don't want to just show them everything that I do. But if you're not in that class and you want to see my solutions, just send me a note and I'm okay to send that to you, no problem. Okay. Okay, so let's get to it. Popular votes. Let's start with that. Popular vote. So you have an election, 2 candidates. The one that we've received less than, okay, you have an election with more than 2 candidates. Sometimes the winner can receive less than the majority of the votes. So given the results of the election, can you determine the winner and whether the winner received more than half the votes? Okay, so that's the problem. You have T, which is at most 500 test cases. The first line of each test case contains a single integer n that tells you how many candidates there are. Then there are n lines, each line telling you how many votes each person received. There are at least 2 candidates and no more than 10. Each candidate will will not receive more than 50,000 votes. There will be at least 1 vote cast. And then you are supposed to write one of 3 possible answers. It can say a majority winner followed by the candidate number. If the winner receives more than half the votes. Otherwise, if there's a winner and that person does not receive more than half the votes, you say minority winner. And then maybe there's no single candidate that has more vote than others, and then you say no winner. And the candidate numbers are 1, 2, 3, 4 up to n. Okay, so let's just quickly look at the first case. 4 means there are 4 cases. Then 3 means the first case is 3 people, and the votes for the 3 people are 10, 21, and 10. Okay, so the winner, of course, is number 2 because 21 votes. And then you look at the total is 41. So 41, half of 41 is 20.5. So 21 is more than half. So this is a majority winner. Next one, 3 people again, 20, 10, and 10. So 20 is the winner, but the 20, it's just half. It's not more than half, it's just half. So it's a minority winner. In the third case, everybody has the same vote, so there's no winner. And then the last one, the number 4 is the winner. And the total is, I guess in this case, 90. So 45 is once again, just exactly half, not more than half. So it's minority. Okay, so here we are. How are we going to do this? And I think for the most part, it is not hard to do, but maybe it's hard to do it quickly. Right? How do people do it in 5 minutes? Perhaps you can ask. So the first thing, I said that I'm not going to show any code, but I'm just going to kind of explain how you would do this. So in main, what I would do in main, okay, I'm not using perfect C++. So I read in the number of cases. And then, of course, I just do a loop. Okay, so you have to declare your stuff if you want. I might not declare everything and write perfect C++ here, but you can fill in the blanks. And then maybe I just do solve. So I typically like to do this so that I solve each case in a single procedure. I don't put everything in here. For simple problems like this, probably doesn't matter, but maybe it's good practice. And then in solve, what do I do, right? I have a bunch of votes. So ins n, c in n, and now I have to read the votes. So what do I read the votes into? It says that there are at most 10 people. So I'm just going to put an array called v, and then do a loop. And read it into the vote. Now, the question then is, what do we have to do, right? We have to figure out, is there a winner? And if there's a winner, is it minority and majority? So how do we know if there's a winner? First, there are many ways, but basically you have to figure out who has the maximum vote. Now, figure out the maximum, the number basic, and you can loop through the thing and you can keep a running maximum. Or if you want, STL in algorithms, there's something called max element. So you can go max element v plus 10, no, sorry, plus n will return a pointer to the maximum element in the array. If there are multiple, it can return any of them. And because it's an iterator or pointer, star will actually give you the value. So maybe I say capital M is equals to this. That's would be maximum vote. And then I can say, well, is there a winner? Well, I can just loop through if I want and ask how many there are, right? Maybe this maximum occurs just once, or maybe this maximum occur multiple times. So another STL function allows you to, sorry, n, and then m allows you to count in an array how many times you see this thing. How many times in this array you see m, and if the count is equals to, or greater than, let's just say greater than 1, then you say no winner, and then you're done. Otherwise, so else, so if like this, else, then you have to say, okay, you can figure out who the winner is by, I guess if you want to actually, maybe instead of starring it, I can say index. So index, but then I have, because it's a pointer, I have to subtract the beginning of the array. So for those of you that don't know, if you have an array, v, the name of the array actually is also acts as a pointer to the first element. So 0, 1, 2, 3, whatever. And if the pointer, if you have a pointer that points to this element, so if this is some pointer p, then p minus the beginning of the array will give you exactly the index that you want. So max elements gives you the pointer, minus the beginning of the array gives you the index. And then here, I guess I would say instead of m, so I would say m is equals to v index. And then, so why do I need to know the index? Because I need to print it if there's a winner. So anyway, now I need to know if m it's greater than total over 2, then it's majority. Otherwise, it's minority. So how do you get total? Well, again, you just add up all the things in this array. Another way to add it up, there's another STL command that allows you to add things up. And that's accumulate. So you can say total equals to accumulate v plus n, and then you accumulate from 0. So that will add up the total of the array. Now, I wrote a lot of these STL things because if you know them, then it's just one line. If you didn't know how to do this, if you didn't know STL, you could just write a for loop for each one of those and do the same thing, right? What other things I want to say? Total divide by 2 is a little bit dangerous. Why is total divide by 2 a bit dangerous? Anybody?
If it's an integer, it won't be account for the fraction.
Right. So whenever I divide by something, integer division, I always have to ask, do I have to worry about integer divisions and getting truncated? Okay. So let's think about this, right? So divide by 2, what can happen? Basically, it's either even or odd. Total can be even or odd. Those are the things that can happen. So if it's 10 over 2, so let's say just pick a random even number 10. 10 divided by 2 is 5. So if you want to be more than half, you want to be more than 5. That's okay. What if with 9? 9 divided by 2 is 4. The real half is 4.5. But if you're bigger than 4, then you're also bigger than 4.5 because m is an integer. So basically it's fine, but you should always stop and think, are we fine, or do I have to worry about this or not? Right? If you don't like that, you can say 2.0, that forces a floating point division, and then you don't have to worry about the rounding. Okay. Anyway, so maybe I'm saying too much for a simple problem, but I do want to sort of show you how I would do it quickly. Again, if you don't know all these fancy STL functions, I guess I would suggest that you learn a little bit at a time because they're very useful, but you can always write an if statement, right? Okay, so I'm going to stop talking about this problem for now. Any questions about this one?
I guess for the STL, is there ever kind of a limit on what you can use? Because
Well,
like I was
only
kind of doing it all manual.
yeah, no, the only limit is what's in the library. So so look up your favorite C++ site. So C++, actually, why didn't just do C++ STL documentation, especially because now we're doing online contests. You can use any reference material. So look up your favorite reference site. So STL has containers, arrays you probably never use, but double-ended queue, linked lists, maps, and so on. Queues and sets. If you're just starting out 2620, maybe none of these words mean anything to you. But after 2620, and certainly after 3620, many of these words you will know what they mean. And then these are ways for you to organize the data and store data, look them up, and so on. And then outside of containers, I think it must be under other. There are lots of things that you can use. For example, complex numbers, something called bit set, which sometimes we use. But the most of the things are in this thing called algorithm. What is this? Add. Yeah, I don't want to see add. Okay, algorithm. So for example, find is a linear search. Count is something that we just did. Count the number of times something appears in a range. There's copy, there's other things, reverse, sorting you never do yourself, min elements, max elements, etc. Okay, now of course you have to know how to use these things. That's part of the issue. And most of the time when they say in a range, it always takes sort of two iterators. One that's specified at the beginning and one that's specified at the end. And C++, the way that they specify beginning and end is maybe a little bit strange if you're not used to it. So if you have an array or other containers, but we'll just talk about, let's say an array now. So here array it's 0. How many elements did I draw? 0, 1, 2, 3, up to 9. So there are 10 elements. So if this is an array A, then A is also pointed to the beginning of the array. And if you want to operate on this array, so let's say you want to sort this array, let's say this is an integer array, you want to sort them, then you say sort A, and then A plus 10. Now A plus 10, where does that put you? A plus 10 means start from A and move forward by 10 elements. So A plus 10, it's here. And you might say, well, why are we accessing out of bounds of the array? And in C++, the way that you specify a range, you always start at the first element of the range, and you always stop one past the end. That's how C++ specify things. And so you also read in many documentation, they would say that the range is first, comma, last, and then a round bracket. And if you remember your high school math or something like that, if they give you an interval like this, that means it starts at 2. You look at the number line, you start at 2, 3, and then they draw something like that. It goes from 2 to 3 and all the way, but not including 4. So it goes from 2, 3, but not including 4. So here it goes from 0 up to, but not including 10. Okay, so it does take a little bit of getting used to if this is the first time you use STL to specify arrays and ranges. But the good thing is every single function in STL specifies things in exactly the same way. So once you know how to do sort, you know how to do count, you know how to do everything that involves an array. It's all the same. Okay. Okay. So now the second problem Now what is the second problem B to do? And if you look at the actual contest, it would turn out no. The winning team took 7 tries to do it. Our own U of L team back in 2015 can never do it after 3 tries. Another team, Calgary, managed to do it in 2 tries, and then a whole pile of teams tried it many, many times and never getting it. So B is something that I'm going to defer for now. I'm not going to talk about this. The next problem I talk about, it's J. I've been everywhere, man. Okay, so Alice travels a lot for her work. Each time she travels, she visits a single city before returning home. Someone recently asked her, how many different cities have you visited for work? Thankfully, she kept a log of her trips, helped Alice figure out the number of cities she has visited at least once. Okay, so first line has positive integer t up to 50, which are the number of test cases. Then first line of each test case also contain a single positive integer n, indicating the number of trips. Then n lines each n following lines describe the trips. The I such line simply contains the name of the city she visited. They only have simple names. Only city names contain only lowercase letters, have at least 1 letter, no spaces. So like this. Number of trips is at most 100. No city name contains 20 characters, blah, blah, blah. So everything is kind of small. For each test case, simply output a line containing a single integer that is the number of distinct cities. So for example, in this list, this 7 lists, there are 4 distinct cities, I guess, Saskatoon, Toronto, Winnipeg, and Vancouver. And then the last one, there's only, even though there's 3 cities, there's only 1 distinct one. Okay, so that's the problem. In other words, you're given a bunch of stuff. You need to know how many unique items there are. There are many ways to do this because the problems are so small. I mean, if you want, right, you can actually just take this as an array of string. For each one, you can scan the rest of it and see if it's unique, or you find a duplicate and then you can cross out the duplicate and so on and so forth. But it's actually much easier than that if you know the right, I guess, setup. Basically, you have a bunch of items. So a bunch of items. How many unique ones? That's the question. So if you remember, I don't know when you learned this, your math 2000 or computer science 1820. When do you keep track of a bunch of things and you don't care, you only care about unique stuff? It's a set, right? You probably learn about sets of numbers. So if you have duplicates, you remove the duplicates, but really set of anything. And as soon as you know this, and as soon as you know that set is in STL, you're basically done. Why? Because you just declare a set of string, and you call it S. And then for each word that you get, so I don't know, so C and I equal to 0, I less than N, I plus plus, and then maybe you have a city name. So so string city, you read city. Now you can do this. You can use this to read because they told you that there are no spaces in the city names. If there's spaces in the city names, then this will only read the first part up to the first space. So then you have to do something else. But because they're trying to be very nice to you, you don't have to worry about this. We'll just get the city name. And then you just say S, just throw it into the set. That's it. So a C++ set allows you to insert things and just it will automatically take care of the duplicates. You don't have to worry about it at all. If it decides that you have if it knows that you have a duplicate and knows that it doesn't have to insert it, it won't insert it for you. And then at the end, you just ask how big is this set, S dot size, and then you're done. Now, for those of you that are new and don't know STL, I suppose you can store this in an array. You can try to search to weed out the duplicates and so on. But I think that it's really worth your while to learn all these data structures in C++. because it's going to save your time so much. What else do I want to say? Anything else I want to say? Yeah, I don't really have much more to say about this problem. Any questions? Okay, there's something in the chat. What is in the chat? Floating number. Oh, this must be before. Okay, the only other thing that I want to say is maybe you might want to know, how long what is the complexity of this algorithm? This is obviously n iterations, right? N iterations. And then the question is, what about inserting something into a set? And for those of you that know, it's basically big O of log of n, where n is the size of the set. So now I'm kind of reusing the n, right? So n is the number of items. N is also the size of the set. Why? Because if you have 100 items, then the set is at most 100. It can be much smaller, but it's at most. And because I'm using big O, it's just an upper bound anyway. And so altogether, it's at most, at worst, big O of n log n. I know that for this problem, n is so small that it's hardly worth bothering. But with this algorithm, even if n is like 1,000,000, it would still be fast enough. Okay, because n log n for 1,000,000 is really not that big. All right. Any questions about this one? Okay, so now the next problem that's easy, supposedly, is problem D. So let's go to problem D. Scaling recipe. This is actually from a cookbook that I have. It's a very scientific cookbook, by the way. So it's a recipe, is a list of ingredients and a set of instructions to prepare a dish. Often written for a particular number of portions. If you have a recipe for 4 portions and you want to make 6, then you can. Then it turns out that simply multiplying the amounts for each ingredients by 1.5, it's often wrong. And the reason is that the original recipe may have been rounded to the nearest spoon, gram, etc., and the rounding error is actually magnified when you scale a recipe. So there are some recipes that specifically designed that allows you to scale properly. And these recipes are developed using something called the baker's percentages. So each ingredient is listed not only by weight, but also as a percentage relative to some main ingredient. The main ingredient will always have 100% percentage. Note that the sum of the baker's percentage from all ingredients is greater than 100, and that the baker's percentage of some ingredients may exceed 100. So here, there's an example of, I don't even know what this is. So olive oil is 50.9 gram, and it's supposed to be 11.2%. Beef, it's 453.6 grams, and that's the main ingredient. That's the main ingredient, and everything else is sort of relative to that. So if you decide to use, I don't know, 1,000 grams of beef, then you should multiply 1,000 by 2.5 to get the amount of onions, etc. So it says, to scale a recipe, determine the scaling factor by dividing the number of desired portions by the number of portions for which the recipe is written. So this thing has 4 portions and you want 6 portions, then the scaling factor is 1.5. Multiply the weights of the main ingredients with 100% baker's percentage by the scaling factor. That's the scale weight of the main ingredients. Calculate the scale weight of every other ingredient by multiplying its baker's percentage by the scaled weight of the main ingredient. So once you decide to use 1,000 grams here, then 18.2% of 1,000 would be the raisins and so on. So basically, it's just a bookkeeping exercise and doing the calculations, right? So first line, again, there's a number of cases up to 1,000. Each case starts with up to 20 different ingredients. For this recipe, how many portion is designed for? and then how many portions do you actually want to make. And then you have a bunch of lines that tells you the name of the ingredient, the weight of the ingredients in grams, and then percentages. All these numbers are floating point numbers with exactly 1 digit after the decimal place. Each recipe will have only one ingredient with a baker's percentage of 100, and then you're supposed to produce the output. So let's just go here, 6 ingredients. This recipe makes 4 portions. You want to make 20 portions. So you need to multiply this by 5. Okay, you multiply this by 5, and then everybody else, you know, onions is 250% of beef. You work that out and so on. Everything is 1 decimal place. And that's it, okay? So it is really just a bookkeeping exercise, I guess. You have to have an array that stores all the ingredient names, all the actual weights, and then all the percentages. And in fact, these weights here are completely irrelevant. They are not used by any calculator. Only weight that is used is the one that is 100%. So you have to figure out which one is 100%, because that's the one that got scaled. And then after that, the scaled one is going to be used along with the percentages to do all the other stuff. So in some way, that's it. There's nothing more to that. You have to be able to round things properly. So, you know, you have your main ingredients. That's called main ingredient weight. So call it, I don't know, W. So W have to multiply by the desired portion. So I call it desired portion divided by the, I guess they call it D in the problem statement, divided by P, the portions that the recipe is for. And that's the scaled weights for the main ingredient. And then every other ingredient would be, so this is the main ingredient weight, scaled weight. Every other ingredient would be the scaled weight times the baker's percentage. So it'll be the percentage, I'll just write baker percentage divided by 100. Like this. Now, again, if all of these things that you have, so the question is, what are you storing these? That this is an integer. This is an integer. This, I guess, is a double. So this should be a double. And similarly, this is a double. And this is double. And this is an integer. So here, this is one place where you can have problems, right? If you don't do things properly, then D divided by P will be rounded down, and then you don't get what you want. And then if you want to print something to 1 decimal place, you'd say cout fix. So fix means don't use scientific notation. Set precision 1, that means set precision. That means use 1 decimal place. And then finally, the number that you're trying to print. Okay, and then maybe you'd use a new line or whatever if you want a new line. Okay, so that's how you print that. Having said that, okay, having said that, there are things that maybe instead of using doubles, maybe we could have used integers. In this problem, it doesn't actually matter. But it turns out that actually you don't actually even need to use doubles. Okay, why? Because they tell you that every number is going to be some number with exactly 1 decimal place. So what can you do? You can actually use 2 integers and just say cin arrow A, some character to eat the dots like this. So A would get this, the part before the dots. The CH would get the dots, and B would get the 4. And now the actual value that you want could be A times 10 plus 4 plus B. So in V, in this case, it's 1,234, which is 10 times too much. Okay, everything is going to be 10 times too much. So now this part is still integers, but this one, if you use this way of doing things and reading the Baker's percentage, because BP is 10 times too much, you just divide by 1,000 instead. And that would be the same thing. So why are we doing this? Because when you use floating point numbers like doubles and floats and so on, everything that you do is potentially subject to rounding error. And for this problem, because you're doing such simple calculations, it doesn't matter. But if you're doing calculations, a lot of calculations, repeated calculations, adding a bunch of numbers together, the rounding errors can accumulate. And you might actually get a wrong answer, even though all your calculations are rounded correctly each time. On the other hand, if you convert all your calculations to integers, there is no possibility of round off errors. So as long as you're sure how you're doing things and make sure that you account for that, everything is 10 times more, then here you don't divide by actual, I don't know, maybe you divide by 1,000 here like this until the very end. Okay, and then until the very end, because then you only have one final step that can give you a round off error. Okay, anyway, for this problem, it makes no difference because it's so simple. But I just want to point out this technique in case you run into something else that might require this. Okay, any questions about this? Okay, so those are the 3 easiest problems in this set. And now we look at, again, hang on, let me just quickly see who is actually here. Julie, oh, the only person in here is the only person in here that's also in my computer graphics class, Caleb. Is there anybody else? Because I'm about to tell you how to do an assignment question from computer graphics. Space junk. Okay, so now I'm jumping to a problem that's a little bit harder. Space junk is problem E. And as you can see, problem E is not solved by a lot of teams, but it's also not solved by very few teams. Even somebody down here managed to solve it after 7 tries. So 10 teams solved it. It's not the easiest, it's not the hardest. So what is this? No. Okay, so space junk. You have a spacecraft and you have a space junk. Both of them are spheres in 3-dimensional space that are traveling in straight lines. Given the current locations of the 2 spheres, as well as the velocity means how fast they're moving and also which way, are they going to collide in the future? Okay, so 2 balls traveling in a certain direction and speed, are they going to collide? Yes or no? That's the question. Okay, the first line of input contains the number of cases up to 500. Then the first line specifies the sphere representing the spacecraft. And then second line specifies the sphere representing the junk. Each sphere specified by 7 integers. What is the 7 integers? X, Y, Z are the center of the location of the center of the sphere. R is the radius of the sphere. And X, Vx, Vy, and Vz is the vector that tells you which way and how fast it's moving. Okay. And it's possible that the vector is 0, 0, 0, meaning that the sphere is actually not moving. It says the absolute value of all the integers at most 100 R is positive. All coordinates and radii are measured in meters and velocities are measured in meters per second. You may assume that the 2 spheres do not touch initially. And then for each case, you have to output when they first collide. If they never collide, then you print no collision. And your answers within 0.01 of the correct answer is acceptable. So basically it allows a little bit of rounding error. Okay, so you have, I'm just going to do the 2-dimensional case because I can't really easily draw the 3-dimensional case in here, but 2-dimensional case, it's more or less the same. Let me get the pen up. Here's a ball 1. and it goes in certain direction. So V, let's call it Vx and Vy, and it has some center x1 and x and y1, and it's some radius r1. You have another ball that's x2 and y2 with some radius r2, and it goes in certain direction, let's say with some velocity v w x and w sub y. Okay, so that's the setup, and the question is, are you going to collide or not? All right, so the first thing that we have to figure out is, how do we represent the motion where this sphere is at any one time? And basically what we're going to do is we're going to track the center. So the center for ball one, it's x1, y1. At time 0 is there. And then at certain time, it's basically how far, which way it travels and how far. It's always time times speed or velocity. Okay, so this tells me at time t, the center of ball one is going to be at this location, whatever time is. You plug it out, you plug in 1 second, 2 seconds, whatever number of second it is. That's the location of ball one. Ball two is similar. Okay, so far? Okay, something in chat. What did people say in chat? Oh, there, oh, STL. Okay, any good resources for learning STL? Okay, sorry, I'm just catching up on chat. STL tutorials. Let's see. I don't know how good these things are. Geeks for Geeks is kind of hit and miss. Sometimes it gives pretty good stuff, and sometimes it gives something that's completely useless. If you know the answer, you'd even say it's wrong. But I think for the most part, for something as simple as this, what's this? Skip. It's reasonable tutorial. So I would say try this. Why are there so many ads? Okay, so anyway, something like this. If you are one of those people that like an actual physical copy of a book, the one that I have used is this one. I actually have a copy of some edition of this particular book in my, is it this book? Maybe not this book. I know I have this book for sure. And I think I also have this book in my office. So I have some books on STL, but you know, if you prefer books, you can buy one of these. But this one is pretty good, actually, C++ standard library. But the only problem is it's 1999. So it's an old version. Anyway, okay. What else is in the chat? Okay, you sometimes use geek cookies. I don't know. Geeks for Geeks sometimes works, sometimes doesn't, because sometimes they give wrong answers. Okay, so now let's go back to my situation with the spheres. Okay, so if I'm only interested in whether the center of the spheres collide, okay, I don't care. So pretend for now that these spheres are just a single dot with radius 0, and they have to collide if the two centers actually exactly collide. Then what do I want? Then I say that x1, y1, I want the two centers to be exactly the same. And so I would basically set the centers to be the same as each other. And because now you have two equations. Why do I say I have two equations even though it looks like one? Because there's an x equation. There's an equation for x, and there's an equation for y. Wait, w x, let me erase. And then it's equals to y2 plus t times wy. All right. So I have two equations, one unknown. So for sure, I have enough information to solve, but in fact, I might not. I might have too much information. So if I solve here, I put all the t's on one side, so it would be t vx minus wx. It's x2 minus x1, so t is equal to x2 minus x1 divided by vx minus wx, like this, right? Does that look about right? Okay, so assuming I haven't screwed up, that's the time. So according to this, it says that at this time t, the x coordinates of the centers would coincide. And then similarly, you can write another equation for t when the y coordinates coincide. And of course, if there's an actual intersection, these two times that you get have to be the same. Otherwise, it won't work, right? Does that kind of make sense? Is there anybody that wants to just scream at me and tell me that this is horribly wrong? And you should. There's something horribly wrong here. If you write this code, it will definitely fail. Why do I say that?
Is that because you're not factoring the radius?
No, I'm only talking about the radius being 0 for now. But even in that case, it's wrong. What is horribly wrong here? Okay, there's something in chat. Floating point rounding. No, that's not the horribly wrong. Floating point is just a little bit wrong, but it's not horribly wrong.
Is it because we made the bases the same?
What do you mean?
Like the starting point, x1 and.
Oh, well, they tell you that initially they don't collide.
Oh, okay.
Okay, when you do such calculations, every single time you do this, what is this? Divide. You must make sure that this thing that you're dividing by is not 0. If the thing that you're dividing by is 0, your answers will be very, very wrong. If it's an integer division and you divide by 0, your program will crash. And that's the good part. If it's floating point, your program will not crash, but it might give you some strange thing. So for example, if you have 5 divided by 0, it might tell you that t is infinity. But if you have 0 divided by 0, it will tell you not a number. And your program will keep going and use these strange quantities in your calculations. And you'll just get more and more wrong as you compute. So what can happen, right? So if Vx and Wx are the same, okay, that means that in terms of x coordinates, in terms of the x velocity, they are basically moving the same way. So how can they ever be the same? It must be if they're ever the same, it must be the case that they are already the same to begin with. Okay, if both of them are moving, let's say +1, if both of them are moving +1 in the x direction all the time, then as long as the original x are different, then it doesn't matter what time it is, they are always going to be separated by the same amount because they're moving at the same speed on x. And if they are already the same to begin with, then they will always be the same. So basically here, when you have Vx minus Wx are the same, those are 0, then you have to look at the top and say, well, either there's never a solution or there's always a solution. So that when you match the two answers for the two equations, you have to be a little bit careful how you match it, right? Because if this one says there's never a solution, then you're done. You don't have to do anything. But if this one says there's always a solution, then you basically say, I just don't care about this anymore. I just solve for t over here, whatever t says here. That's the answer. Provided, again, of course, that you have an exact solution and not either infinite number or no solutions. So I just want to point out that, yeah, even though the math here looks kind of simple, whenever you actually try to divide, anytime that you think about division anywhere, you must ask yourself, can it be 0? And if it can be 0, what should you do about it? Okay, because if you don't, one of the test case out of 1,000 will have this case being Vx minus Wx equals 0 or break, and then you don't know what's happening because you check all your math, everything looks right. Always remember to check division by 0. Okay, so that's a lesson of the day. All right. Okay, but as you said, I pretended that these things have no radius. So what do I do when there's radius? Okay, so now if I think about two balls hitting, okay, so a ball here and a ball here, and they travel towards each other and then they hit. How do they actually hit? They're going to hit when they touch each other. Okay, that's how they hit. When they touch each other, the centers, the distance of the center will always be exactly the same thing as the sum of the two radii. So instead of just saying that the centers are exactly the same, now I have to be a little bit more sophisticated with my equation. Okay, so what is this? What is the equation now? Okay, so I need to know, I need to say that the distance between centers, it's equals to R1 plus R2. So how do I say the distance between center? Well, if I have the center X and Y, okay, we're using X1 and Y1 and X2 and Y2. If these are the 2 points, then the distance is the square root of X2 minus X1 squared plus Y2 minus Y1 squared. This is Euclidean algorithm. Oh, sorry, the Euclidean, no, what am I trying to say? Pythagoras theorem is what I'm trying to say. Too many Greek people that I got confused. Pythagoras theorem. Okay, so I need to say the square root of the centers. It's just square root of the distance between centers is R1 plus I2. Now, what is the centers? Well, the centers are this expression. So for example, this one, it's actually X2 plus T times Wx. So I have to plug all of that in. And then there's this square root thing, which is always a pain in the ass. So the easiest thing to do is actually square both sides. So then you don't have to worry about the square roots. So on this side is R1 plus R2 squared. It might look complicated, but remember that R1 and R2 are just fixed numbers that you're given. So this is at the end just a number. Over here, X2, it's this. And my X1 is this. All square. And then plus the Y2 plus TWY minus Y1 minus plus TW VY squared, like this. Okay, now remember, even though there are lots of things lots of variables going on, remember that everything in these equations are known, given as the input. The only thing that's not known is T. Everything else is just a number. Okay. So you're solving T for this equation. So what do? You expand everything. And if you want, you can actually rewrite. I'm just going to expand this part. You can expand the other part in a similar way. This is Y2 minus Y1. I'm just going to rewrite this. Minus T times WY minus VY. And then all square, like this. And then there'll be basically the Y2 minus Y1 square. And then minus 2 times Y2 minus Y1. So this is the time that you have to do some algebra. And then plus T square, WY minus VY square. Assuming I haven't screwed up, I'm missing a T. I'm missing a T here. Okay, so anyway, you're going to get some kind of quadratic in T. You're going to get some quadratic in T over here. You collect all the things that have no T's. You collect all the things that have T, all the things that have T square, move it all together. And eventually you should be able to write it as a times t squared plus bt plus c equal to 0, where a, b, and c are some expressions involving y2, y1, x1, x2, x1, and all those things. Okay, so all of that algebraic manipulation, it's a little bit, none of this is computer work. They're just, you're doing on paper. At some point, you will figure out the expressions for a, b, and c. And now you go back to wherever you learn quadratic equations in, I don't know, high school or whatever. Then you know that t, the solution is negative b plus or minus square root of b squared minus 4ac divided by 0. Oh, sorry, what the heck did I just say? Divide by 2a, like this. Okay, so now, first question, can a be 0? I told you every time you divide, you ask yourself, can a be 0? It turns out that it's possible, if you work out the expression, it turns out that it's possible that a is 0. And in that case, it turns out that a lot of things are equal. The starting point might be equal or whatever. And it would basically, based on the assumption that the two spheres never collide initially, you basically will say that if a is equal to 0, there are no solutions, because it means that they just collided originally. Okay, so basically a can never really happen. Okay, so now when you solve a quadratic equation, what can happen? If you remember from, I don't know, wherever you learned this from, grade 10, grade 11, who knows?
Imaginary numbers?
Well, okay, we don't want imaginary numbers, but imaginary numbers, if you go that route, it's a possibility, but we want real answers. So what does that mean? That means they can tell you that there's no root, so that would be your imaginary case, but no real root. In that case, b squared minus 4ac can be negative, right? So if you see this, before you do this square root thing, you see this, you're done. You just say no solution, no collision. Or it can be one root, okay, or it can be two roots. Now, having roots doesn't automatically give you a solution, because the root can be negative. It can be that if you run the thing backward in time, they collide, but they don't collide if you go forward. So if the root is negative, no collision either. So in order for you to collision, the root has to be positive. And it's possible that when you have two roots, both roots are positive. And in that case, you pick the smallest one because you want the first time that this occurs. So anyway, I guess I've kind of shown you how this can be done. Of course, I didn't show you any code, but this problem is really not about coding. This problem is about figuring out what to do, figure out all the math. And once you know exactly what the math is, well, then it's not so difficult to write something like this to evaluate it. Okay. So I guess what I want to say, the lesson for this, what's the moral of the story? When you have geometric objects and you try to move them around, you try to do things with them, in this case, collide them and so on, very often it's about writing equations that define the objects and then solving equations in some way. It's almost 90% of the time it's like this. So this is more of a, I guess you can call it a math problem that requires a implementation at the end. But for the most part, it is a math problem. Okay, any questions about this one? Now let's see, which other one do I want to talk about? Classy problem. Classy problem is in the actual contest. Where's classy problem? I think it's problem E. Problem F. Quite a few teams solved it eventually. Not a lot, but maybe half the teams. 29 teams out of 52. So let's just take a look at what that is. I think, Caleb, you tried it in our practice, right? And you were unable to do it. Were you getting wrong answers or something else?
I don't know what it was. On all the cases I could think of to test, it worked. So there's something I just wasn't thinking of.
Okay, so feel free to send after the meeting, feel free to send things to me. I actually happen to have all the test data because this is a contest that I was part of as a judge. So I have all the test data. I know it. I can run your program on all the test data and tell you exactly which case fails. Okay, so there are these people that are in different classes of society. So you can be in middle class, you can be upper class and lower class, but that would be a little bit too unrefined, I guess. So within each of the classes, you can divide it further into threes and so on. So for example, mom, it's in the middle class, but within the middle class, she's in the lower third, and within that, she's in the upper third, and within that, she's in the upper third. Okay, so it's a little bit complicated. Dad is in the middle class. Within that, he's in the lower class, lower third, and then within that, he's in the middle third, middle third, middle third, etc. Okay, so you got these three people, sorry, 5 people, and you are supposed to sort these people from the highest class to the lowest class. So Queen Elizabeth here, it's the highest one, upper, 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 and so on. Now, notice that they don't all have the same number of upper and lower and middle, right? Some have 4, some have 5, some have even 2. So how do you know, right? So you have to know, the first thing is you have to remember that this time we have to read things from right to left, because the first one on the right tells you which of the third it is. There's a top, middle, and lower, and then after that you subdivide. So one of the first things to realize is that in order for you to compare 2 people, let's say you have middle, mom is whatever, upper, upper, lower, middle, and chair, it's lower, lower. You don't even have to look at the rest because you know that mom is in the middle third and chair is in the lower third. So you immediately know that mom is higher than chair. When you have to actually look at something, it's when they're tied, right? Middle, middle, mom and dad are both middle, middle. So then you have to look at the next one. Lower, lower, so they're the same. So you have to look at the next one. Upper, middle. So mom is in a higher class than dad. Okay. What about the situation? What if you have something like this? So somebody's in upper, and then another person that's in upper, I can't spell upper. Upper, let's say lower. Who is higher? Okay, so this is upper, and this is lower, upper. Okay, so this person up to this first 2, or the last 2, if you want to read it backwards, they're the same. But then this one is in the lower one, and this one is unspecified. So what does the problem say? There are 3 main classes, blah, blah, blah. All upper class, okay. Within a class like middle, upper, there can be further distinction as well, blah, blah, blah. When comparing classes, once you have reached the lowest level of detail, you should assume that all further classes are the same as the middle level of the previous level of detail. So upper classes are middle, upper equivalents. So basically, whenever you need to add more things to make the length the same, they're telling you, just pretend that you add middle. Okay, so what can you do, right? So there are a number of problems. The first problem is, how do you parse this damn thing? Okay, so you're given basically a name, and you're given a name, and then you're given this funny string, and then you're given the word class. The class, you can just read it and throw it away. You don't really care. The only thing that matters is this one. It's always separated by spaces. It's separated by dashes. So what I would do is I would first, if this is a string, I would first get rid of all the dashes with spaces. So this is how you can use, this is an STL command again. We place all the things in this range, the beginning of the string to the end of the string. What do I replace? I replace the character minus by the character, I'll just write it, this is space, by the character space. And this will take this string and change all of these to a space. Now that I have a strings with words separated by spaces, I could use an iString stream to pick it apart. So what is iString stream for those of you that don't know? It's basically like cin, but instead of somebody typing from the keyboard, you initialize it with the contents of a string. So now, if my string is middle space, upper, then when I do something like ISS, arrow, arrow, word 1, word 2, and word 3, then it will actually read in middle as W1, middle, upper, like this. That's these three. Okay. So that's how I would pick it apart. Now you don't know that they're exactly 3, so you'll just basically do a while loop that keep reading strings as long as there's no end of file, and end of file in this case means end of the string. They also tell you what they tell you that each name contains at most 30 lowercase characters. So you know, because there are 30 lowercase letters, the number of items can never be more than 30. It's actually a lot less, but 30 is for sure an upper bound. You can never have more than 30 items in the upper lower. So let's say it's 30, doesn't really matter. So you can write a loop that reads all of them into an array of 30, at most 30. And then if you, let's say you want to read an array of 30, but you only have 5 items, well, you can fill the rest with middles, right? And actually, the other thing is, it's actually a good idea to read it in backwards. Because, so you can say everything else is middle, like this. Why is it good? Because when you have multiple arrays of this type from different people, you're gonna first look at the rightmost thing, which if you store it backwards, it's the leftmost things. So you basically just look at it from the first element. If they're different, then you're done. You know which one is bigger. Otherwise, you go to the next one and so on. The other thing that I would do is actually just make them, when I just convert it to a number. So upper, let's say I converted to 2, middle, I converted to 1, and lower, I converted 0. So now this would just be an array of numbers, right? 2, 1, 0, 0, 1, 1, 1, or whatever. Okay, so I just have an array of numbers. So now what? Okay, so I have a bunch of names and an array of numbers. So how am I going to store this? I'm going to actually use a structure or a class if you want. Doesn't really matter. Let's just call it a, I don't know, person. One of the few times I actually would use an object-oriented programming. And inside, so struct basically is a class, but everything is public. So there's no encapsulation. So let's see here. So there's an int, let's call it A up to 30. That would be my sequence of class labels, the numbers 0, 1, 2. And then I would also have a name, right? Because I need to know the name of the person. And I'll have some function that read into a person, right? Variable. And then somewhere I would say person, I don't know, P bracket, I don't remember how many persons there can be, up to 100 people. So P100. And then I will just, once I know how many people there are, then I'll just do a loop. pi.read. And that would read each person, convert it into an array, and so on. And now, what I want to do is I want to sort. So P plus N. and have it sorted so that everything that basically sorted in whichever way you want, increasing, decreasing order, doesn't matter. So let's say increasing order. So smallest to largest. I know that you want to print backwards, but you can either sort it in increasing order and then print it backwards, or you can sort it backwards and print it forward. Doesn't really matter. I'm using increasing order because that's the standard C++ way. And the way that you do it is you have to write your custom comparison operator. Operator less than, and this is, I write a lot of things here like this. Okay, hang on, let me just draw a line here. So const. I have to write all of these. I cannot skip any of these words or it won't compile. So basically I'm comparing myself versus this one, the parameter, and I return true if myself should come before the other one and vice versa. And if I should not come before this other person, I say no. So what is it that I want to do, right? I want to compare this array, my array versus your array, p.a. And I want to say, let's look at this one. If they're not the same, then whichever one is smaller, that's the smaller one. If they're the same, then I got to look at the next one. And basically I keep going as long as they're the same. As soon as I find something that's not the same, then I look at which one it is. And then decide whether I should be smaller, which one is smaller. And so you can write a for loop that's as long as a while loop if you want, that basically goes for as long as the two matching entries are the same. And as long as they're different, then you quit and return something. You can do that. But again, if you know STL, you'll discover that you just have to call an STL function. So STL, there's something, what we do here, it's what is called lexicographical compare. All right. So, lexicographical compare. Take two ranges, first range, second range, and then checks if the first element, the first range is lexicographically less than the second range. What does that mean? Two ranges are compared element by element. The first mismatching elements define which range is lexicographically less or greater than the other. Blah, blah, blah. Okay, so actually you can write this yourself if you want, or you can just call this function and then be done with it. So just say return lexicographical underscore compare, and then bracket what? So it'd be my array and then your array. Like this. And that's it. And the sort will automatically take care of itself because it will use the operator to go from smallest to largest. And then, well, okay, if you want to print things backwards from largest to smallest, then you have to print things from back to forward. Or if you want, you can then call reverse. So this is another STL function that just basically take an array and reverse it. And now you can print it forward. Okay, so I guess the theme here, maybe if you haven't noticed it already, I used a lot of STL functions to save time. It's not that I don't know how to write reverse, right? It's probably one of those things that you learn in 1620 as an exercise. Your first programming course, how do you reverse an array? How do you know if a string is a palindrome and things like that, right? It's not that I don't know how to write these things, but when I write something like this, it's hard to get wrong and it's much faster usually. You might say, well, it's not that much, it's not that fast to type lexicographical compare, but it's hard to get wrong. And if you get wrong because you mistype this, the compiler would catch it. It's not a logic error, right? So it makes your code easier to understand, easier to write, faster to get working. So if you're starting out, this can be a bit overwhelming, the way that I'm using STL left, right, and center. But I think that the only way that you can really learn this is by jumping into this pool deep, head first, and just use it. If you can keep reading things, but until you actually use it, you won't know what's going on. So that's why I'm throwing all these STL out here, just to get you to be aware of what you can do. Okay, do you have any idea what you did wrong, Caleb? After the explanation.
Not really.
Okay, well, feel free to send things to me later, and I can have a look. Okay. Okay. Now we're getting to the point where things. Oh, maybe we're still not quite to the point where things are really tricky. The next one. Which one is the next one? H, magical 3. I think this is the next one. Or I, matrix p-pad. They're about the same, 11, 14. Okay, magical 3, I do want to talk about for sure. Okay, so there's some kind of funny talks about how 3 is a nice number. But anyway, there's a story that doesn't really matter. And then here, almost all integers can be represented as a number that ends in 3 in some numeric base, sometimes in more than one way. So consider the number 11. It says in base 8, it can be represented as 13, right? 8 plus 3. And also in base 4 is 23. So for this problem, you will find the smallest base for given number so that the number's representation in that base ends in 3. Okay, so base 2, base 3, base 4, and so on. And you cannot have base 2 and base 3 because there's no digit 3 in base 2 and base 3. So the smallest base you can possibly have is 4. And then you try to see if you try all the different bases, I guess, and say, if you write the number in that base, is the last digit 3. So each line of input contains one non-negative integer n. The value n equals 0% the end of the input and should not be processed. All integers are less than 2 to the 31. Why is that important? Because that's the largest possible 32-bit integer. So if you use the word int, that's the largest possible number you can store. There are no more than 1,000 cases, basically. For each non-zero value of n, in the input, print on a single line the smallest base for which the number has the representation that ends in 3. If there's no such space, print no such space. Okay. So when can you have no such space? Well, it turns out that if you have the number 2, you can, well, if the number is 1 or 2, there's no way you can ever have a digit 3, no matter what. Okay, no matter what base you choose. What about other numbers? Well, maybe that's a little bit harder to say. So what to do? Well, this is where you have to be a bit smarter. You might say, okay, you're given n, and you want to find a base b so that the last digit in base b is exactly 3. So what does that mean, right? So if you remember when you learn conversion from one base to another, how do you get the last digit? Usually to get the last digit, or how do you conversion, your algorithm usually start by saying n mod b. Take the remainder when you divide by b. That's the first digit that you get, but you get the digits backwards. So that's the last digit. And then to get the next digit, you would then divide. So n equals to n divided by b. And then you keep going in a loop to get the next second last digit and so on and so forth until n is 0. Okay, we don't actually care about the whole thing. We just care about the last digit. So we can ignore everything else after the first line. So on surface, it seems to be really easy. You are given this as the input. You don't know what the base is, but you know that the base is at least 4. So try base equals to 4, and divide by 4, remainder is it 3? If not, try 5, 6, 7, 8, 9, and so on until it works. The problem, of course, is that this can take a long time if you have to test a lot of B's. And it will turn out that, especially if there's no such case, when do you actually stop? You have to go all the way to n, maybe. Okay, because n mod n is 0, and n mod anything else is bigger than n. It's just n. Of course, there's some special cases when n is small, but let's not worry about that for now. So we need a better way than just trying all possible bases. So what should we do? What should we do? Well, we have to now think about what this means. We want to know if n % b it's equals to 3. We want to be a little bit smarter than just plugging in different values of b to check to try to get this to work. Instead of just trying all the values of b, it's like solving an equation. You don't always just try all possible values, plug it in, and see if the equation holds. You try to actually figure out b directly somehow. So now what does that mean? Okay, so now you have to think about what does n divided by b taking the remainder means. N divided by b remainder, you have to remember when you divide, there are always two parts. There's the quotient and there's the remainder. And the relationship between the quotient and remainder is like this. And the thing that you're dividing into, it's always the thing that you're dividing by times the quotient plus the remainder. Okay, this is a division algorithm, one of the first things that you learn when you learn about division, at least in university anyway. And we want this to be 3. We want R to be 3, right? So now maybe we're getting a little bit further, because what we want to do is we want to solve for B. So B, maybe let me write it another way. So n minus 3 is B times Q, right? Now there's a problem. Maybe you say, well, okay, n is known, of course, 3 is known, but now I have 2 unknowns, right? I have 1 equation and 2 unknowns. How do I do this? There might be many solutions, and it's true. But what it's saying is that n minus 3 is the product of 2 things. What are you allowed to put in here? Anything, right? So you're allowed to, for Q, you're allowed to put in any positive integers. B, you're allowed to put in any positive integers bigger than 4, bigger than or equal to 4. And we're saying, can you write n times n minus 3 as a product of 2 things with some constraint about B being at least 4? In other words, what I'm asking is, what are the divisors of n minus 3? Which ones do I want? I want the divisors of n minus 3 that are at least 4. And I want the smallest divisor of n minus 3. Because I want the smallest b that works. And then, whatever that turns out to be, if I have any divisor that is at least 4, right, then the smallest one will be the b that I'm looking for. So this becomes a matter of factoring a number. Okay. Before I go on any further, does that make sense? Let's see, is there any chat? No. Okay. So this somehow get converted into a problem of factoring. Factoring number n minus 3. And n, remember they tell you, is less than or equal to 2 to the 31 minus 1. Okay. For some reason, I lost my mouse cursor. Why do I? Okay, so now I don't know where I'm writing anymore. Okay, I'll just guess. Okay, so 2 to the, this is the integer range of what you have to factor. So how do I factor? Well, how do you factor if you don't know any better? You try. You try. Can you divide by 2? Divide by 3? Divide by 4, 5, 6, 7, and so on. And for each one, you ask, it's n% d equal to 0. And if so, you found a divisor. Right? So whatever that number, sorry, n minus 3. I'm trying to, that should be n minus 3. I'm factoring n minus 3. So if any one of these d's that I'm trying divides even into n minus 3, I'm done. But the question is, when do I stop? What if n minus 3 is a prime number, right? So what are the things that you know is that whatever, so let's say you're trying to test, I don't know, divide, is what are the divisors of 100? Well, there's 1 actually you don't really care. So forget about 1 for now. So there's 2, there's 3, 4, 5, 6, 7, 8, 9, 10. And at this point, this is a square root of 100. You can stop. Why do I say you can stop? It's not because that you don't have any more divisors, but any divisors that you have must match something that is less than the square root. Right? 25, 50. And because you're looking for half, you're looking for the smallest factor, maybe you don't need to worry about that too much, although if you have some really tricky thing where you have something like, I don't know, 6 or something like that, then the smallest factor is actually not what you want. You want is 3 because, oh wait, no, hang on. What number should I use? Because you want a divisor that's at least 4. So maybe you have a number like this, 2 times, let's say 3 times 5. So you have 15. You don't want to stop at square root of 15, which is 4, less than 4, because even though you found a factor, you actually want the bigger one in this case. But anyway, the point is, once you have all the factors that are less than or equal to the square root, you can get the rest of it easily. You don't have to go all the way. So if your numbers is up to 2 to the 31, then the square root of that number, it's definitely less than 2 to the 16, and which is 65,000 roughly. And 65,000 iterations is very fast. You don't have to worry about it. So basically you write a loop like this that checks, I don't know, for d equals to, let's say 2, and then d is less than or equal to square root of n minus 3, d plus plus. Then if n minus 3% d equals to 0, then you found a divisor. Okay, then you found a divisor, but maybe if d, so then you have to check both d and n minus 3 over d, because those are the 2 divisors that comes out in this pair, and then see which one is smaller and which one is at least 4 and things like that. Now, you don't want to do this the way that I wrote it, because you have this square root, which can introduce errors. So what you do is you do the same trick that we did before, square both sides to get rid of the square root. Now you just have integer division, integer calculations. There are no round of errors. But then you have a different problem. Even though n minus 3, it's up to 2 to the 31, roughly. This d could be, you can have 2 numbers that are both close to 2 to the 16 or so, multiplying to overflow 2 to the 32, 2 to the 31. So this d squared may overflow. So what you have to do is that over here, instead of using a normal integer for d, you would use a 64-bit integer to make sure that there's no overflow. And that would be the way that you would do a normal trial division up to square root of a number. And then this way, all of this thing that I talked about doesn't work if n is less than 3, because if n is 3 or less, then n minus 3, it's either negative or 0, and then everything is divisible. So for those cases, for any, if they give you the input as 2 and 3 and 1, those are special cases, but there are only 3 cases, so you can deal with them separately if you want. Okay, so that's all I want to say about this problem. Does that make sense? Any questions about this? So this is, we're getting more to the algorithmic and mathematical stuff here. Matrix keypad, do I want to say anything? Okay, I don't want to say anything here. I'll just let people look at it and try to do it if they want. I want to say a couple of harder problems. The first one is one that actually nobody did in the actual contest. Rubik's Revenge. Okay, so you have this a 2-dimensional Rubik's Cube, I guess you call it. And what's happening in this 2-dimensional Rubik's Cube? You have 16 squares, 4 red, 4 green, 4 blue, and 4 yellow. And in each move, you're allowed to slide 1 row left or right, or 1 column up or down. So in this case, you slide the second column down. So the green comes down 1 step, the blue comes down 1 step, the yellow comes down 1 step, but the red gets shifted and go back to the top. So it's kind of like a circle. Over here, you move 1 step to the right. So the green moves to the right spot, the 2 reds move 1 step over, and the red on this edge comes back to the left side, the left edge. Anyway, so those are the moves that you're allowed to make. So every step you're allowed to make to move this, any 1 row left or right, or any 1 column up or down. And your goal is to solve the puzzle in exactly this order. Top row is red, second row is green, and then blue and yellow. And then they also tell you, they did tell you one thing: all possible configurations are solvable in less than 13 moves. So it says basically, if you try to solve something and you try all possible 12 moves and you couldn't do anything, then you know that it cannot be solved. Okay, so that's basically what they tell you. And then you have to give the minimum number of moves needed to solve the given puzzle. You don't have to actually say how to solve the puzzle, just how many moves. Okay, so this is a general puzzle problem. What does this puzzle have? There's some kind of configuration or states that represent, at each point, what does the puzzle look like? And a configuration of states basically means that if you know this information, okay, if whatever information you need to record about the puzzle, if you have this information, you can kind of go away for a while, come back to it, pick it up from exactly where you left off. That's what a configuration means. So in this case, configuration is just whatever the puzzle looks like at a particular time. Then you have moves. Okay, so in this case, you have 4 rows, you have 4 columns. So there are 8 possible places, things that you can do, but each one of them you can do either up or down or left or right. So once you decide which row or column you want to operate on, there are 2 things you can do. So altogether, there's 6. From each configuration, there's 16 different things you can do. So what do you do, right? The standard thing to do is you have some start configuration. You represent this somehow. Then you generate all 16 possible moves, which will lead you to some other 16 different configurations. From each one of those, you generate 16 possible moves. Some of them might lead you back to things that you have seen before. okay, and so on. And you just keep on doing this graph until one of these states, it's the soft configuration. So conceptually, you build this graph, you do this exploration in the graph, and then when you find this node, you figure out what is the shortest path from start to soft. So conceptually, if you have a graph where every single edge is counted in exactly the same amount, and you want to know how many steps it takes to get from start to soft, you use breadth first search. Okay, so conceptually, you have some way to represent the configuration. So in this case, probably like an array of 4x4 array of characters. Then you have a way to get you to the next possible moves, 16 of them. For each one, you ask, have I seen this before? If so, you don't explore anymore. You ask, is it the soft configuration? If so, you're done. Otherwise, you push them all in the queue, which is what the breadth first search does, and then you just run the breadth first search algorithm. Okay, but there's a problem. All of this works if the graph is small. Okay, the graph is small, you can do it. If the graph is not small, then this can be really, really slow, right? So how bad is it? You have 16 squares, and there are 4 colors, each with 4 things. So if you ask how many different possible configurations there are, it's 16 factorial divided by 4 factorial, 4 factorial, 4 factorial, 4 factorial. So to remove the duplicates. And I don't remember what this is, but it's a really large number. It's large enough that you don't actually want to do this. Okay, so no go. So if you work out a problem and you consider this number of nodes in a graph, and the number is actually reasonable, let's say to the order of tens of millions, then you just do it. There's nothing to worry about. However, this is not going to work so well. So what? So what do we do? So another way to think about it is, okay, maybe we don't need to consider everything because they told you that you can do things in 12 moves or less. Okay, so you start, then you do 16 steps, you generate 16 possibilities. Each one of them can generate 16 of them. And you're told that this can go on for no more than 12 steps. So some of the things you don't even have to consider. If you cannot reach in 12 steps, you don't have to do it. That's what they tell you. So how bad is it? Well, the first layer, there's 1 node, then there's 16, then there's 16 square. Now, some of them may be duplicates, so maybe it's not really 16 square, but let's be a little bit more conservative. And then eventually, basically 16 to the 12th. And you add that all up and you once again realize this is way too much, hopeless. You can't do this. Now, what is the trick here? And this is one thing that is very common in many of these puzzles. The fact is that for each move, there is an opposite move. So what do I mean by that? If you decide to slot opposite, how do I spell opposite correctly? Opposite. So what do I mean when I say there's an opposite move? Okay, lost my mouse cursor, so I'm trying to figure out where I'm writing. So if you decide to slide the first row to the left 1 step, if the next step you slide the first row back to the right, then you're kind of undoing the move. You can cancel it. And in these cases, you can think, okay, I'm trying to do a search. Where's my mouse? Okay. I'm trying to do a search from the start and then through some steps to get to the soft state. But equivalently, I can also start from the solved state and work backwards to find the input state. It's completely equivalent. I can do both ways, right? I can start from the beginning and move forward until I find this, until I solve the problem, or I can start from the solved solution and move backward until I get the input. Okay, so what's the point? It's exactly the same problem. There's nothing to be gained. Now, what's to be gained is that you know that here, from start to end, or from end to start, whichever way you look at it, there are the most 12 steps. So what does that mean? That means if you go this way for half the steps, if you go 6 steps and you look at all the possible positions that you can reach in 6 steps or less. If you go this way and look at all the things that you can reach in 6 steps or less. Now you ask, is there anything in common? Right? Maybe this configuration, it's reached by here in 5 steps, and it's reached by here in 4 steps. If you can find anything in common here, that means you can glue the 2 solutions together to go from start to here in 5 steps, and then from that point to solve in 4 steps. And if you cannot find it, that means that there are no solutions of 12 steps or fewer, because these are all the things that you can reach in 12 steps from either end. So what you do is you generate all the things that you can reach from the front, from the start in 6 steps. You generate all the things that you can reach from the back, going backwards in 6 steps, store them in some data structure that allows you to easily match them up. So, okay, so I'm intentionally, I guess, going a little bit vague here, because the people that can actually do this, you probably don't need me to tell you how to use a map or a set. So you can probably figure that out on your own. And you match them up, and then you take the minimum. So why is this much better? This is sometimes called meet in the middle algorithm. So you're searching. Before we're talking about 12 steps, and 12 step we said it's basically like 12 to the 16 to the 12, which is pretty big. But now instead I'm only doing 6 steps, so 16 to the 6. This is, remember, 16 to anything, or any base to some power. This is exponential growth. So if you reduce the power by a lot, that actually makes it a lot more feasible. And you do this 16 to the 6 twice, but twice is not really a big deal. It's just a constant. The most important thing is it's not 16 to the 12. And then you have to do a little bit of work to match them up. But again, most algorithm, if you use a set or something, you can do this in n log n time, where n is 16 to the 6. So what is 16 to the 6, right? So pull up a calculator. Okay, 16 to the 12, first of all, it's this much, hopeless. Actually, it's worse than that, because it's 1 plus 16 plus 16 square plus 16 cube and so on. And this is geometric series. So it's actually more like 16 to the 13 divided by 15 or something like that. But anyway, we'll just pretend it's 16 square, 12. 16 to the 6 is what? 16 million. All of a sudden, it is much more reasonable. In this problem, they tell you that there is how much time limit? 8 seconds. Actually, it's a lot. 16 million, a couple of seconds, which is more than enough. So yeah, I think if I remember correctly, we decided in the judging team to code a particularly inefficient solution, just to make sure that if somebody used a very slow implementation of the right algorithm, it will still pass. But if they use a wrong algorithm, there's just absolutely no way. So anyway, I know that this problem is meant, this discussion is meant for the more advanced people, but I want to break it down into something that start from a simple fact that this looks like a search problem, but the standard search is too slow. And then if you use this thing called meet in the middle, it basically allows you to cut the running time substantially. So I do understand, yeah, for those of you that are not more advanced, you probably have no clue what I just said, but I mean, we're getting to the harder problems. Okay, so now let's see here. What else do I have here? There are other problems that I haven't talked about yet. Flipping cards, amazing race, Rubik's Revenge, bundles of joy. So I kind of went over the easier problems, right? I kind of skipped over some of the middle problem, if you want to call it that. Flipping cards I didn't talk about, amazing race, because probably there's not a lot of point talking about this for the junior people, and for the senior people, I guess they already solved it. The only one that I didn't really say, and it's really maybe much harder, is bundles of joy. And in the wheel contest, exactly one team solved it. No, yeah, exactly one team solved it. I'm just going to say, if you want help, if you want to do this problem, if you want help, we can talk privately. I don't want to take up time saying something that the majority of people would have no idea what I'm talking about. So anyway, I'll stop here for this week. And next week, I have posted another contest. This time is East Central North America Regional. That's actually one of the strongest regions in North America. There's University of Waterloo, University of Toronto, Carnegie Mellon University, and so on. The problem set is here. Is okay. The one that you can use, the one that you can submit to is a different one that I put in Discord. But this is the actual contest site at the time, and you can see the actual scoreboard if you wish, right? And you know, there clearly is 3 problems that lots of teams can solve, so maybe you should look into those first. The rings, squawk virus, and what's on the grill. And then there's some problems that maybe you don't really want to touch. A and H, only 2 teams solved it. Sorry, only the first team solved it, the winning team. And then there's some other problems that are not so easy either. Okay, anyway, so I'll stop here, stop share. So I know there are a lot of new people today, and that's good, that's great. If you have any comments about, you know, how you think this session was going, let me know.